Start recording, so we are good. Okay, so we are going to talk about relations today, but before we go there, are there any questions about Cantor's pairing function, which is quote unquote function G that we talked about in the previous class? No questions? Are there any questions about the derivation of Cantor's function and the inverse function of Cantor's function? Nope. All right. Well, so I cannot really see this particular screen on my screen here. I could not get the screens to overlap. So that means, I might need to take a look at the screen, by turning around. Um, I know this stuff for the most part already, but I cannot see what you guys are seeing unless I turn around. So it can be a little bit challenging. So we'll see. I think we can get it to work. Let me see. Where's my mouse cursor? Oh, that is not nice because I cannot find my mouse cursor. Uh, let me. Okay, there we go. All right, so we're gonna go through relation, but before we start on the detail of relation, let me first describe why it is important to understand recursion, not recursion, but relations. So a relation, from your perspective, is comparison. Okay, less than or less than or equal to is a relation because it relates real numbers or doubles or integers. So let me turn off the one that I'm not using. And, oh, all right. So we're gonna turn off this one and turn that one back on. Yep, there you go. Okay. All right. But why is that important? So when was the last time you have to write your own sorting function to sort objects? So we are not talking about integers or doubles. We are talking about objects. So when was the last time that you had to write your own sorting function in order to sort an array of objects and they're representing something, okay, like maybe players in a video game. So when was the last time you had to do something like that? And do you think that you have to do it in industry? If you graduate and you move on to become a software engineer, do you think you need to implement your own sorting function? The answer is no. The answer is no, because most languages would give you an array type that has a sort method. Okay. But now the question is, but how do you sort an array of objects? I mean, sorting an array of integers is like, yeah, we know how to order the integers. Sorting an array of doubles, oh, that's pretty easy too, because we understand how does one double, how the value of one double compares to the value of another double. Question? Um, so so there are a few ways to look at this. The first one is, okay. Let me see if I can get this to work because it's the challenge is I tend to lose my cursor, so I don't know where my cursor is right now, and I have to move it back to here, and I don't want it to go too far. So there we go. Okay, so we can take a look at JavaScript. Okay, array type. Okay, so when you look at array of JavaScript, you can see that it has sort already as a method. So every array has a sort method. But the thing about the sort method here is you still have to supply it with something. So when you look at sort, okay, and you have to give it a compare function because otherwise it doesn't know how to order what is the proper way to compare items in the array. Does that make sense? Now, if you have, as I said, if you have an array of integers, then you go like, yeah, I don't need to supply my own function, because it is pretty clear, what less than means, or less than or equal to mean. When you deal with real numbers, kind of the same thing. But Those would not be the usual things that you need to deal with because what if you have an array of objects and the objects are representing something that does not have a single value for comparing? Looking, I can give you an example. Since most of you are gamers or have played some kind of video game where they want to keep track of your player of the week, right? Player of the month, who is the most valuable player for this particular team. That requires sorting, right? So the question now is, if I give you two objects, okay, each one representing a player, how do you compare those two players or those two objects and tell me which one is less than or equal to which one? Okay. Are you going to look at the amount of time they spend on the game, or the amount of money they spend on the game, or the number of people, the other players that they bring into this game? How are you going to do the comparison? Or how other players vote about this particular player? Okay, friendly, not friendly, salty, you know, really helpful with the team. How do you sort? How do you compare? Hmm? But what number are we talking about? Because a player has multiple numbers associated. There's no particular way to do it. It's up to you as a developer, right? Up to the company. So if you work for Valve or if you work for who's the publisher of League of Legends? Hmm? Riot, okay? So if you work for Riot, you go like, okay, so you ask your boss, okay, how are we selecting the player of the week? Your boss may say, well, I think it is important to look at how much money they spend on skins, okay? Because we want to promote people spending money on useless skins, okay? Collect all 64 skins for a particular player when it doesn't really help to enhance the game at all, okay? So maybe that's a priority. Or maybe your boss goes like, well, we want people who bring in other players. Okay, we want people who just have enough influence so they bring in other players. Okay, or maybe your boss says, I want to select the player who is the friendliest, okay, who get the most upvotes from other players. So we don't know exactly what is quote unquote the best metric, or maybe it's a combination of all of the above. Okay, 80% comes from how much money they spend, 20% comes from how many other players they bring into the game. Okay, but whatever metric you're gonna use, you better make sure it is a total order, which means you would not end up in a situation where I give you two players and I ask you rank these two players and tell me which one is better, okay, to be the player of the month, and you end up going like, I really cannot tell you which one is better. You don't want to end up in that situation. Is that okay? Is that okay? All right. So I'm changing the ordering of how concepts are introduced in this class, in this particular topic. So I'm going to go straight to a beer commercial. It's funny. And let me see, is my speaker up? My speaker is up, but it's connected to my Bluetooth. It's a beer commercial, okay? So you can probably just watch the movie and not hear the sound. It'll still be okay, even though hearing the sound is better. So YouTube, and then we want to look for beer commercial, smooth versus rich. All right. Oh, beer. That tells you how much I drink beer. Okay, Michelob. Think this is. I think this is a good one. We'll give it a try. Yeah, because the audio is sent to my audio here. Okay. So the point is one is smooth and the other one is rich, and the beer is both. So that's the whole point of this commercial, is to promote the beer. All right. So are we doing okay so far with the message of the commercial? So the rich guy is really rich, right? With all the, AV setting and whatnot, but not smooth. Okay, he is just not smooth. And then the other guy is super smooth, but he is so poor that he had to take, the woman to a Best Buy to go like, okay, let's watch a movie here. So that's, smooth but not rich. Okay. So in this movie, or in this commercial, it illustrates the concept of comparison, right? And we are going to define the relation called at least as attractive as, okay? So I'm not promoting beer. I'm not promoting whether rich is a good thing or smooth is a good thing. I'm only using the beer commercial as an example. Okay, I just want to make sure it's very clear. I'm not promoting any particular value. I'm just using it as an example. Okay. So let me use a, yeah, this is not handy because I can't really easily move around here. All right, so I think I can use my drive and go to 440 and go to the shared folder. So this way, whatever document I create, you can actually see it too. There we go. And then we'll create a new spreadsheet. Okay, so new sheet, and I'll name it with today's date, making sure it's easy to find. So today's date is 2025 0915. There we go. All right. So we are now trying to make a table to define, what is at least as attractive as what else. Okay. So we have rich and smooth. Then we have just rich but not smooth. Then we have smooth but not rich. And then we have tack, who is neither, not rich and not smooth. And we'll do the same thing over here, rich and smooth, rich, smooth, and then we have tack. There we go. So we are trying to check a box if the column is at least as attractive as the row. Are we good so far? So since I said at least as, right? So that means, the diagonal is going to have the check marks because they are basically saying, equal. Are we good so far? And now we can check out the other items. So we can now say, is rich at least as attractive as rich and smooth? No, according to the commercial, it's not. Okay, but the other way around, it is. So rich and smooth is at least as attractive as rich alone by itself. So we put a check mark here, and we put a check mark over here, and everyone is at least as attractive as tack. So we also put a check mark here, a check mark here, and also a check mark here. Are we good so far? All right. But you can see that there are certain things that we simply do not know how they order. Specifically, when you compare rich and smooth alone, the commercial did not indicate whatsoever whether rich by itself is at least as attractive as smooth alone or the other way around. So that means there are situations where you can be presented two objects and you really do not know how they're supposed to be ordered. Now, when I said we do not know how they're supposed to be ordered, I mean you cannot even establish that they are the same. Okay, so you can see that the diagonal line would be things that are the same, and then the other check marks would be things that are actually not the same, but still be ranked. But we are missing this one, and we are also missing this one more. because when you compare, so we have these two are the ones that are problematic. So let me just put a question mark over the ones that are basically problematic because we don't know how they're supposed to be ordered. So what we end up with here is we have a relation that is not totally ordered. It is partially ordered, which means for certain things we can establish ordering, but there are certain items, in here that we simply cannot establish ordering. So with that, you cannot sort these objects because it is not totally ordered. Are we good so far in terms of understanding why it is important to understand relations? Because we want to understand how each and every item, everything in the column and also the row, how they relate to each other. But in this particular case, there are certain things we simply do not know how they're supposed to be ordered. Are we good so far? All right. Okay, so now getting back to the notes, okay, now that we understand the importance of what we are talking about, so now we can go back here and talk about what exactly is a relation. The first thing is something that looks like something that we already know, but it's actually used in a slightly different context, and it is also different from what we think we already know. So a relation R that is defined over a set X has to be a subset of the Cartesian product between the set X and itself. Okay, so there's no domain versus codomain. Okay, because in the case of a function, this has to be a subset of the Cartesian product between the domain and the codomain. Now we only have one single set. Okay, so for every R that is a subset of X Cartesian product with X, the R can be seen as a relation defined over X. So is that terminology doing okay? Are we understanding that terminology? Okay. So if a particular element, which is a two tuple, and this time the first item of the two tuple and the second item of the two tuple, they come from the same set. Okay, because we don't have the differentiation between the domain versus a codomain. So if the two tuple does exist, then we can use this notation. In other words, if xy in parentheses does exist in R, then we use this notation to say that x relates to y using R as a relation. That's just a notation. Are we still doing okay so far in terms of, the notations? We good? All right. All right. So that's basically, what we mean by a relation. It is very loose. In other words, with a function, we got a few attached, we have a few requirements. One, the function has to be a subset of the Cartesian product between the domain and the codomain. Okay, that's easy. Okay, we got something like this too in relations. But we have a different requirement for functions. For every element in the domain, it has to map to one and only one thing in the codomain. We don't have anything like that in relation. Are we doing okay so far? Okay, because I want to make sure that we can differentiate between what a function is versus what a relation is. A relation is far more flexible in terms of what can be a member of the subset of the Cartesian product. So somebody is going to say, so can it be an empty set, right? Because an empty set is definitely a subset of every possible set. The answer is, yeah, it can be an empty set. You can have an empty relation, meaning that it is an empty set. Nothing relates to anything in that particular relation. Are we still doing okay so far? Okay, all right. So now we can present a few examples. Okay, so this is an example of less than. So I'm using less than not only as a symbol, okay, which is an infix symbol here, which says a is one less than two, and the answer is true. It is true that one is less than two. But the other way to say that, which is a very odd and weird way to say exactly the same thing, is one two as a tuple is an element of a set that we name less than. Is that okay? So in the second case, the second bullet point, less than is not seen as an operator. It is seen as quote unquote the name of a set that turns out to be the the subset of the Cartesian product, in this case of integer Cartesian product with integer. Are we still doing okay so far? Just in terms of the notation. Are we good? Yep. Well, if it depends on what name you choose to use for the set. I choose to use this really weird name for the set in this case. R is the name of the set, which is the Cartesian product between hmm? Whatever name you want to use. You can use it either as an infix notation, or you can say a tuple, a two tuple is an element of that set. Mhm. All right. So these two are equivalent statements, okay, in this particular case. All right. So this is a fairly well-known relation, less than, equal to, those are pretty well known. So now we're going to look at some random, relation. So in this case, I define X to have only the elements A, B, C, D. I define R to be a subset of X Cartesian product with itself. Well, first of all, do we all agree that this particular R is a subset of the Cartesian product of X and itself? And how do we know? How do we check? Well, we look at each and every single item, and then we ask the question of, does this, is every first item of the two tuple coming from X? A is from X, A is from X, B is also from X, D is from X, B is also from X. Okay, that meets the first requirement. Then we look at the second item of each and every two tuple and ask the same question. Are they also coming from X? A is coming from X, B is coming from X, C is coming from X, D is coming from X, A is also coming from X. So now it has met both requirements. So now we know that this R is in fact a subset of the Cartesian product of X and itself. Is that okay? And that's the only requirement to be a relation. Okay, there's no such thing as every element has to map to one and only one, or everything has to be used up, or uniqueness. Nope, none of that. All right. So using this particular example, we can now say A R B is true because A does relate to B because AB as a two tuple is in R. So we use R here because the name of the set is R. So if I name the set Q, then we will say AQB is true. Okay, so whatever name you choose as the set, you can use the name of the set, quote unquote, as an infix. Are we doing okay so far? Yep, yep, yep. And we can also say whether a two tuple BC is in R or not. In this case, it is true because we can see that BC as a two tuple is in fact in R. We can also say BRB is false because B does not relate to B in R. And for the same reason, we can also say DC as an element of R is also false. So in this case, I'm just illustrating that these are the two notations. We can use the infix notation, which implies element of, or we can just spell out the two tuple and ask, is that an element of the relation? Okay, so it's a notational kind of thing. And I'm going to close this window because otherwise it shows the name or the ID of the monitor. All right. So now we are pretty much done with um, the basic definition of a relation over a particular set. Okay. So if we say that R is a relation defined over X, all it is saying is R is a subset of the Cartesian product of X and itself. All right. So now we move on to the more obscure stuff, okay, which is my favorite part. Now we can say whether a relation R defined over X is reflexive or not. Okay, so the definition is a relation R over a set X is reflexive if and only if the following is true. So this is a quantified statement. It is universally quantified. So if I were to spell it out, okay, what it really is saying is for every element in X, that element has to relate to itself by R. So that's the only requirement for a relation to be reflexive. Okay. So now we can go through a few examples and see if see if see if you think they are um, reflexive or not. And for this part, let me see what is the best way to do it. I think I'm gonna use Joplin for this. Mm, Maybe just plain editor. So we'll see whether this works out or not. All right. All right. So here we go. And we first have to define X. So just for simplicity, we just say that A, B, C are the elements of X. And now we have to define R. We'll start with this one. What if R is an empty set? In this case, is R, which is defined over X, is it reflexive or not? Does it meet the requirement that A relates to A and B relates to B and C relates to C? What do you think? It is not. That is correct. Okay. So this is not reflexive. Okay. So we're going to write down this is not reflexive. What if we define R to be A and that's it? Is that reflexive? It is not reflexive. What about B? Does B relate to itself? No. How about C? Does C relate to itself? No. So if you thought this one is reflexive, then the concept that you might need to clarify is the universal quantifier. Because the universal quantifier says A has to relate to itself, and B has to relate to B, and C has to relate to C. But since we only have A relating to A, B relates to B is false. C relates to C is also false. So we end up with a conjunction of true and false and false. So the whole thing is false. Okay, so that means, oh, okay, so if we want to have, so this is also not reflexive based on how we define X. So if we want to define something that is reflexive, okay, I think we got it, right? So we'll have AA, BB, and CC in it. So this one is reflexive because obviously A relates to A and B relates to B and C relates to C. So when universally quantified, okay, because this is the important part, this is still reflexive. So I'm going to throw another case at this. Okay, so we're going to say, what if we are looking at this one here? Okay, we still got A relating to A, B relates to B, C relates to C, but I'm going to throw in A also relates to C. Is that reflexive? Why is it not reflexive? Huh? It is reflexive. That is correct. Because the key question is A still relating to A? Yes. And is B still relating to B? Yes. Is C still relating to C? Yes. So that extra thing AC does not affect whether this particular R, the last row, is reflexive or not. It is still reflexive. You can add additional elements to the R to the relation. It is still reflexive. Yes. We evaluate whether this is true or not. Oh, you mean just so okay, so this is still reflexive. So in a test, I typically will ask you only tell me why it is not reflexive, and you have to tell me, oh, because it doesn't have this. Yep. Yes. All right. Yep, that is correct. If we only have AABB, then it is still not reflexive. Okay. Now, based on those questions, I think it is really important that we understand what this means. Okay. What is the for all? So in this particular case, based on how we define the set X, we basically say R is reflexive if and only if ARA and, okay, I'm going to use the special symbol here, BRB and CRC. Is that okay? That is the conjunction that has to be true in order for R to be reflexive. So this is how we can look at a universally quantified expression and convert it into a conjunction. Now, this is possible only because we only got three elements in X. Okay, so obviously, if X has a whole lot of elements, this may not be a viable option to spell out exactly what does it mean to be universally quantified that for all E in X, EE is in R. But this time we can spell it out just because, well, we only got three elements in X. Are we good so far? Okay, all right. Shall we move on to symmetric? Okay. So things get a little bit more dicey as we move down the list, but this one is still not too bad. I'm going to make this one always on top because I need to scroll the other screen. Okay. So symmetric is defined as, okay, for all EF in X, which means there's no restriction of how you choose the E or F. Okay. They can be the same if this also happen to be. So in this case, we need EF in R if and only if FE is in R. So that is the definition of symmetric. Okay, so we can go back to some of the previous examples. Okay, so this time, so let me just kind of copy and paste a bunch of these. Okay, down here. Okay, but this time we are not, we don't care whether something is reflexive or not. So we get rid of all the conclusions because this time we want to know whether they are symmetric or not. So we get rid of all the reflexive and replace, and then we have to figure out whether each one is symmetric or not. We'll start with the empty set. Is that symmetric? It is symmetric. Okay, so how do we figure out whether it is symmetric or not? In other words, Tech, can you give me something that looks like this so that we can evaluate whether this particular with respect to this particular definition of set X, whether something is symmetric or not? Well, I can do it, but it's going to be quite tedious. Okay, because what you need to do is to say R is symmetric if and only if, okay, the following are all true. The following are all true. Okay, so we're going to start with E equals to A, E equals to B, E equals to C, and then we have E equals F equals to A, F equals to B, F equals to C, and then the same thing with the other one. In other words, we have 9 specific cases to consider. Okay, and then we ask, okay, so now tell me what is the value of E F in R, okay, EF in R, if and only if FE is in R. Okay, so can someone tell me whether this is true or not? When E is A, F is also A, and R is empty. We are still looking at we are still trying to apply to the case when R is an empty set. So tell me if R is empty, whether this particular if and only if is true or not. Why is it false? But neither do we have AA. We are missing AA in R, but we're also missing AA in R. So now the question is, do you remember what if and only if means or equivalence? No? All right. We got some studying to do. When did we define the truth table of if and only if, also known as equivalence? Day one of this entire semester. You can, do you want to look it up in your own notes? This is why we need to take notes, and this is also why it is handy to put all the definitions to one single place because it becomes easier to look it up. Okay, so that means, so this tells me one thing, okay, it tells me the importance of understanding the symbols. Okay, this is an operator. So, okay, so then the if and only if is true, right? Okay, that is correct. Okay, very good. So we say, okay, this is true. Okay, that is true. Okay, what about this one? Um, okay, remember R is empty. It has nothing. So that means, oh, this one has to be false too. Has to be true. Sorry, it has to be true, and this one also has to be true. In fact, all of them have to be true because R is empty. It has nothing in it. So anytime you ask, hey, is blah 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 in R? The answer is no, it is not. And since we are asking the same kind of question on both sides of the if and only if, so that means both sides of the if and only if can only be false. False, if and only if false is true. So that means for all nine possible cases, they're all true, which means one thing, R when R is an empty set, it is symmetric. Are we doing okay so far? We good? All right. So now we move on to the next one. Okay, we look at R being defined as only having AA in it. Is it symmetric? Is it symmetric? Yep, it is symmetric. What if R is defined to have AA, BB, CC in it? Is it symmetric? It is still symmetric. What if R is defined to be the last one? No. It is not symmetric because AC is in it, but CA is not. In fact, I can pinpoint exactly where it is going to give us the false. So it will give us a false when we are here, and one more time when we are here. Because when E equals to A, F equals to C, this will evaluate to false. Because only one side is a true, the other side is a false. But because we also ask a question when E equals to C and F equal to A, this particular row would also give us a false. Well, one false is enough because we need all nine of these to be true in order for the universally quantified expression to be true. So if we find one case that it is false, we automatically come to the conclusion that it is not symmetric. Okay. So what if we are to put something back in it? Okay. So what if we take this R and then we go like, yeah, let's make it a little bit bigger. Or better yet, okay, better yet, I make it so that we don't have all of these. We keep one of them, and then we just kind of go like, yeah, well, we'll put CA in it. Oops, CA. So now for this particular R, is it symmetric? It is symmetric. Okay, so this one is symmetric even though it is not reflexive. Are we good so far? All right. So equivalence is actually pretty easy to deal with because equivalence means the if and only if is true, even when both sides are the same. They can both be true, they can both be false. So in a certain way, it is relatively easy to understand. Question? If you add AA to R, it will still be reflexive. Hmm? Nope, it is not because you're still missing BB. So if you just add AA here, it is still it would not be reflexive, but it is symmetric because we are missing BB, and if you're missing BB, then it is not reflexive. Okay, so so because you're asking that question, so that means you really have to understand what that means. In other words, it boils down to what does it mean when we say for every E in X, blah 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 has to be true. Yes. Nope, let's not think of those terms because they are not actually related. Yep. All right. So are we good with symmetric, or do you guys want to give me an example and I can tell you whether it is symmetric or not? Are we all good with the concept? Okay. So now we're going to deal with transitive. This is how it is defined. So this time it's a little bit more complex because this time we are saying, oh, for every way to choose E and for every way to choose F and for every way to choose G, so that E is an element of X, F is an element of X, and G is an element of X, we need to make sure this portion is true. Is that okay? So when we only have three elements in X, we have 27 items to evaluate because E can be A, B, or C, F can be A, B, or C, and then G can also A, B, and C. So you have 27 cases to consider, but for every single case, you better make sure this part is true. Are we okay in terms of the concept? We good? All right. So now we go back and take a look at some of our examples, and then we ask, is that transitive or not? So we are gonna, so for this one, I'm not gonna spell out all 27 cases. I mean, you guys can make a table if you want to, but I think, you guys get the idea of what those 27 cases look like. So we're gonna take a look at the specific R's that we have been looking at, starting with the easy one. Is an empty relation automatically transitive? Okay, I see the nods, and it is. Okay, how do we know? Because nothing is in R because it's an empty set. So that means this side has to be false. This side is guaranteed false. So the conjunction is also guaranteed false. When the left hand side of an implication is false, the implication is guaranteed to be true. So we know, okay, an empty relation is guaranteed to be transitive, in addition to symmetric, but it is not reflexive. Okay, so let's move on to the next item. Is this one transitive? The answer is yep, it is transitive. Because when the three variables involve anything else, the answer is going to return true. In other words, if any one of E, F, G is not A, then we know the condition that we are evaluating is guaranteed true. How do we know? Because when you look at the element of, one of them has to involve the one that does not have A. Okay, because what did I say? Out of E, F, and G, one of them is not A, right? So if within E, F, G, one of them is not A, so that means within this conjunction, at least one side is guaranteed to be false. If at least one side is false, then the whole thing is false because it's a conjunction, and because the whole thing is on the left-hand side of the implication has to be true. So that's a fairly easy one to work out. Okay. What about this one here? Is that transitive? Yep, this one is still transitive. What about this one? Is that transitive? So it's almost like you have to think of cases where the expression that we have to evaluate is false. Okay. So the question is, if R has AA, BB, CC, and AC in it, can we make this implication false? Hmm? Not for AC, for this entire R, can we make this expression false? Is there a way to choose E, F, G being elements of X such that EF is in R and FG is in R implies EG is in R to make that implication false? What do you think? Well, I'll give you the answer. This is actually the R that I'm highlighting is actually transitive. In other words, all 27 possible cases, they all return true. Okay. So worst case scenario, okay, if you're not really sure what to do, enumerate all 27 cases and evaluate all of those one by one because you will see the pattern emerging. If you don't do that and you just look at this, you may not see the pattern, but if you are to do it, then you will sooner or later, you will actually recognize, oh, so that's what we're looking for. Okay. Well, how about you pick one? So choose what do you want E to be? Okay, so we have A, B, and C, right? Oh, that's easy. So AB is in R is false. So that means it is already true, right? The implication is true already. Yep. But that's how we are evaluating all of the other ones too. We are substituting, and that's why, before I erase that, I said, okay, E equals to A, E equals to B, E equals to C, while E equals to A, F equals to A, F equals to B, F equals to C. In this case, we just have one more layer. We just have one more nesting layer where G equals to A, G equals to B, G equals to C, while E and F are already fixed. So we have a triple loop instead of a double loop, since we have three variables in this case. Are we doing okay so far? All right. No. So which part is challenging us? Say again? Okay. So is it because of the mechanical aspect or is it because of the kind of the meaning part of transitive? Is mechanical? Okay. So let's take a look at an example where it is not transitive. This one is not, yeah, this one is not transitive. You go like, oh, this one is transitive, sorry. My bad, this one is actually transitive. I have to give you one that is not transitive. Okay, so if I take out one of them, it is not transitive. I'm just going to take out AA. Now it is not transitive. So if I already tell you it is not transitive, then you have to think about, okay, so how do we make this expression false? What needs to be E, what needs to be F, and what needs to be G in order for EF in R and FG in R, the whole thing implies EG in R to be false. We want the implication to be false. So the way I would look at this is I would go back to the truth table and I ask, how can an implication be false? Okay, there's only one way to make an implication false. What is it? The left-hand side is true, the right-hand side is false. Okay, so let's look for a case like that, right? So we want EF in R and FG in R to be true, but EG in R to be false. So we are still looking at the last case, okay, the last definition of R, which is right here. Okay, that doesn't give us a lot of choices, right? Anything that involves B is not going to work out, okay, because it's going to be true. Because if EF includes a B in here, that thing in R is going to be false, which means the implication is going to be true. Okay, that's not what we're looking for. We're looking for counter examples, okay? Tell me how to get the values of EFG so that this whole thing is false. So we are really trying to confirm, okay, go find me EF that is actually in R. So we can now say, well, what if we make it AC? In other words, E equals to A and F equals to C. Is that okay? So that will make EF in R to be true. But once we have fixed the value of F, which is what? C, right? That means, oh, we are now looking for C comma something to be in R. And C comma something can either be a CC or a CA. So let's pick CA. So now we have fixed all three variables. E is A, F is C, and then G is A again. Are we good? Okay, so if I were to write that out, okay, so we are looking for a case where E equals to A, F equals to C, then G equals to A again. You plug in those values, right? You go like, okay, AC is in R, that's true. CA is in R, that's true. AA is in R, aha, that is not true. We just made the implication go false in one specific case, but that's all I need. All I need is one case where the implication is false, then the entire universally quantified expression is false. Yes. Hmm. That would be transitive. Hmm. Correct. So let me make it clear. This one is not transitive. So what you're telling me is, what if we have AB, we have BC, and also AC in it? This one is transitive. It is not symmetric, but it's transitive because that's how transitive means. A is less than B and B is less than C, is A less than C? Because we are using B as quote unquote the bridge between the A and the C in that case. Yep. In other words, your typical less than or equal to, greater than or equal to, all of those relative or relational operators, they are all transitive. And same thing with equality, okay? Because if you tell me A equals to B and B equals to C, does that imply A and C are the same? Yep. So even equality is transitive. What about inequality? Inequality is not transitive. A does not equal to B and B does not equal to C. Does that automatically imply A does not equal to C? Nope, because A and C can be the same and B being the only one that is different. Okay, so are we good with transitive? Okay, so this part, okay, the way I describe these properties, I intentionally use the quantified expressions and only using the set notations because we have talked about those already. In fact, they are so dead of a horse, they are now basically looking like hamburger. Yes. You mean with the example? Okay, so let me go back here. Okay, which one do you want to change? CA? That would not be transitive. It would not be transitive anymore because we can make E equal to A, F equal to B, and G equal to C, and AC is now missing. Yep, order does matter. Yep. But I'm going to keep it the way as it was because I want to name that one as transitive. Yep. All right. So now we have something that is awfully confusing because when people think of anti, they mean, oh, it means it's not. No, it is not. It is not. Yes, that's what I said. Anti does not mean it is not. Okay. So anti-symmetric is not the same thing as saying it is not symmetric. Okay, so it is best really just to look at anti-symmetric by its definition instead of trying to semantically process the words and go like, oh, anti means not, and anti-symmetric simply means it is not symmetric. Nope, don't do it. Okay, just just go by the definition. All right. So anti-symmetric also has an implication in it. See, this is our implication. So now we're going to take a look at the ones that we have seen already and see and ask, is that anti-symmetric? In other words, when R is an empty set, is it anti-symmetric? It is automatically anti-symmetric because of the trick that we already used several times. Because if R is empty, so that means this element of and this element of, they are both false, which means the conjunction has to be false, which also means the left-hand side of the implication has to be true, which means the implication itself is true. The left-hand side of the implication is false. Sorry, I think I might have misspoken. So the left-hand side of the implication is guaranteed false, and therefore the implication itself has to return true. Okay, so we now established that one is anti-symmetric. What about this one here? Is that anti-symmetric? So anytime you turn your head and go like it is not something, then you better give me some examples, okay? How are you going to choose the values for E and F so that this entire expression is false? Hmm? So when both are A, okay, let's spell it out. Is AA in R? Is AA in R? Does A equal to A? Okay, so you have true implies true, which is day one. Truth table. And I really remember that I asked you guys to remember the truth tables. Yes. Okay. Any other cases where you might think that you can make the implication itself false? You cannot make the implication false. Okay. So that means whatever R that we are highlighting right now, it only has one single element of AA. It is anti-symmetric. What about the next one? Okay, this one is reflexive, it is symmetric, it is transitive, but is it also antisymmetric? In other words, can you choose E and F to make this expression false? So in a test, okay, well, I wouldn't do it in a test. I would do it, kind of like an exercise, okay? If you don't know by just eyeballing it and go like, okay, I can instinctively tell that this one is or is not antisymmetric, then you go the long way. You go for the scenic route. There are only nine possible cases. You evaluate all nine cases, and by the time you get to probably the fifth one, you already know the pattern. Okay, you go like, oh, okay, so that's what this is about. Okay, so that means for people who cannot just do the eyeball right now and go like, oh yeah, this is definitely anti-symmetric, do the exercise. Okay, just do it, and then at some point you're gonna say, oh, okay, now I understand what I'm looking for in order to say that this particular R is not anti-symmetric. Okay. So I'm telling you, this one is anti-symmetric. The one that's highlighted is anti-symmetric. What about the next one? That is also anti-symmetric. Okay, hmm? It is anti-symmetric. So tell me how you can make it. How? Tell me how you make this implication false. Hmm? Okay. Wait. Okay. So E is A, F is C. AC is in R. Yes, we got that. But is CA in R? So think it through first. Okay, I don't mind people kind of like shooting in the dark as long as I'm not in the room. Yep, but this has nothing to do with curiosity because you have everything that you need to know to evaluate it. You just have to evaluate it first before asking the question. Yep, yep. This one is anti-symmetric. It meets all the requirements. So what do we know about the one that we are highlighting? It is reflexive. It is not symmetric. It is transitive, and it is also anti-symmetric. Yep, that is correct. Once we add Ca, then it is not anti-symmetric anymore. So the next one, oops, where's my cursor? There we go. This one. This one is not anti-symmetric because you can make E equal to A, F equal to C. Is EF in R? Yes. Is FE in R? Yes. Is does E equal to F? No, because one is element A, one is element C. They are not the same. So now we managed to make the left-hand side of the implication true, but the right-hand side of the implication to be false, which is the only case when an implication is false. All right. Then that also makes the next one not antisymmetric. In other words, when we look at this case here, this is also not anti-symmetric because once again, AC and CA are both here. I don't really care what else is here. If AC and CA are both here, then it cannot be anti-symmetric. And what about the last one? What about this one here? Is that anti-symmetric? Well, there's no need to shrug. We just work it out. There are only nine possible cases. Work them out. So, what nine cases are we talking about? E can be A, B, or C. When E is A, F can also be A, B, and C. So we have nine possible cases. You just work them out. Each and every single one. There's no, okay, if you're looking at this and you're shrugging, then you really need to work them out. Because in the process of working out all nine cases, you will start to notice a pattern. But if you don't do it and you just listen to me explaining why this one is anti-symmetric, then you will never develop that ability by on your own to be able to tell what is the pattern that we're looking for. Yes. Hmm? Okay, wait, saying it is anti-symmetric. Wait. Okay, so I think you meant to say it is not anti-symmetric. You cannot use a single case to prove that it is anti-symmetric, but you can use a single case to show me that it is not anti-symmetric. Mm-hmm. 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 Then they not anti-symmetric. That is correct. Yep. All right. Are we addressing your question? Because it's a big conjunction. Yep. Is that hmm? Well, at least initially, okay, because I don't have to go the whole way. I know what pattern I'm looking for. Okay. Yep, exactly. But what pattern you're looking for, that relies on you guys actually spending the time to work out all 9 cases. And then once you do it enough times, you will actually develop the ability to go like, oh, okay, now I know what pattern I'm looking for. There's no shortcut. Well, okay. I never had to look at all the cases, but I'm teaching this class, okay? You guys are not teaching this class. You have not been teaching this class for years. So I would recommend you're working out all the cases. Which brings us to the point of if you are to generate exercises for yourself, okay? So we're going to fix X to be A, B, and C, okay? And you say, okay, I want to test my ability understanding all of these things. How many R's can you possibly generate? In other words, I'm asking, how many test cases can you possibly generate so that you can get an idea of, okay, I think I'm getting it. I'm looking at the number of subsets of the Cartesian product of X with itself. I think we vaguely have dealt with this problem before in one of the function assignments. Hmm? It would be 2 to the power of not 64. That would be a huge number. I would never ask you guys to do something like that. Okay, so how many elements are in the Cartesian product between X and itself? Okay, we got 3 on one side, we got 3 on the other side. So the Cartesian product has how many items? Not 6 squared. Exactly. It's 9 of them, right? And each element or each tuple can either be in or not in R. So that means we have 2 to the power of 9, which is 512 possible cases. But of the 512 cases, many of those are quote unquote symmetric. In other words, you're just looking at, oh, so this used to be A and now it is B, and that used to be C and now it is A, and so on. So many of those cases are actually really the same thing, except we just labeled the elements slightly differently. So the actual unique number of cases is very limited. Okay. So do you guys know how to generate additional examples for yourself to evaluate? Yep, you can certainly do that, and you can avoid things that are actually the same. We're just relabeling the A, B, and the C. Okay, but if you don't know how to do it, then you can have little study teams. Okay, so one person come up with the subset, and then the other person is the one who has to evaluate. Is it reflexive? Is it symmetric? Is it transitive? Is it anti-symmetric? Okay. So it helps to study with somebody else, okay, so that one person can go like, okay, I think this one is super ultra tricky, and then the other person is the one that has to answer. So what if you come up with a particular one and you go like, I'm not really sure whether this one is transitive or not. Okay, so what do you do in that case? In other words, your study buddy gave you a particular R where you are not really sure whether your answer is right or not. So in that case, what are you going to do? Hmm? Test all possible cases. Okay, what is the worst that can happen? There are 27 of those cases for transitive, and that's the only one that is kind of gnarly. All of the other ones only has 9 possible cases. And since you're supposed to spend 2 additional hours for each hour that you're in the lecture, you have what? Okay, each week we have 160 minutes that are in this room. So that means you're supposed to spend 320 minutes outside of this classroom to do all the studying, which includes in this case looking at all the some of the tricky cases. 320 minutes is 6 hours and 20, no, 5 hours. Okay, I cannot do division. 5 hours and 20 minutes. That is a lot of time. So even if you look at something like this one here, and you go like, I'm not sure this one is transitive or not, evaluate all 27 cases. How long do you think that would take you? Okay, let's do an estimate. So this is the most gnarly one because here we have an element of, a conjunction, element of, and then we have an implication. So if I tell you what E, F, G are, how long do you think it would take you to evaluate whether the implication itself is true or not? I think would a minute be about right? Okay, let's say it's a minute. Okay, so in the worst case, it would take you 27 minutes to look through all the cases. And the moment you do this, okay, I would say for most people, by the time you get to like the 12th or the 13th, case of the 27, you will start to notice a pattern. It's like, oh, so that's what it is. And then you would just go like, okay, now I know how to do a mental shortcut to quickly evaluate whether a particular R is transitive or not. But if you don't do it that way, and you're not really sure by eyeballing whether something is transitive or not, then it will still be in that state by the time we get to the first exam, which is not a good situation to be in. Okay, so what am I saying? I'm saying use the time that you have to do some exercises. Okay, it doesn't have to be a graded homework assignment from me. You can also do your own homework assignment. Okay, just like what I just suggested. All right. Um, I'm gonna give you guys one more thing to think about, okay? Which is, but Tech, how do we come up with a random R so that we can actually evaluate it? Okay, so this is the quick way to do it. Get a random generator that can give you a random number between 0 and 511. You got like, what does this have anything to do with generating an R for me to evaluate? What is 512 again? 2 to the power of 9, right? So that means when you look at a number from 0 to 511, if you look at the bits, okay, and when you look at that number as a binary number, it has only zeros and ones. So each bit position corresponds to the presence or the absence of a specific tuple from the Cartesian product. So that would give you a pretty easy mechanism to go like, oh, okay, I'm just going to pick 273. Okay. You look at all the bits. Okay. You find out which ones are the ones in the binary bit pattern. And then you go like, okay, the corresponding two tuples would be in that particular R. And now I'm going to work out, is it reflexive? Is it symmetric? Is it transitive? And is it anti-symmetric? So it's pretty easy to come up with examples for you guys to work through. But you have to do it, okay? Because by going through those examples, one, you will get a much better understanding of the quantifier themselves, because you go like, oh, okay, so we have to go through all of these cases, and every single case has to be true for the quantified expression to be true. Okay. So unless you go through that process, to be tedious, to go like, oh man, this is a lot of work, you don't understand that they all have to be true in order for the quantified expression to be true. Second, when you evaluate all the cases, sooner or later you go like, oh, okay, I have this mental trick that can quickly evaluate whether something is transitive or not because I'm looking for this particular pattern here. Okay, the more you do it before the exam, the quicker you can answer the questions in the exam. It is not a matter of whether you can, it is more of a question of can you do it within the time of the exam. Okay, I have a lot of people complaining to me and go like, but Tech, that is not fair, okay? Because I should have as much time as it takes me to answer the questions. Well, I encourage you to talk to your employer once you're employed and go like, I can do this. Just give me more time. In today's climate, people are even afraid to take vacation days when they have vacation days already accrued. They have weeks and weeks of vacation days, but nobody is taking a vacation. Why? Because the company goes like, oh, so whatever this person is supposed to be doing, nobody's doing it now. And I have this is not a joke. VSP is a relatively local company. Okay, they're not huge. They're kind of big but not huge. For every software engineer position, they get 50,000 applications. That is why people do not take vacations. Yes, you had a question earlier. Somewhere around week 5 and 6. Yep, it is still floating. Yep, it will still be in the week 5 to week 6. We're in week 4 right now, so I'm gonna guess it is the week after next. Yep. All right. I will see you guys on Wednesday. And before we meet on Wednesday, please give yourself some examples to go through. Now, if you go through some of those examples and you go like, oh, so that's all it is about. I get it now. Woohoo! Yes, cool. On the other hand, if you go through some of those examples, like, I'm not sure about this one, then bring them back on Wednesday so that we can evaluate those together. Okay? You good? All right. So I'm going to stop the recorder.